using, forgot to start recording actually. On the other thing. Oh, it is recording. Anyway, that's fine. So, yeah, continuing our recap from last time, using our general form of a boost in one direction, we recovered our previous result that we had obtained concerning the speeds of clocks in relative uniform motion. And then we studied a similar phenomenon, which is the contraction of length, meaning that moving objects are smaller relative to objects at rest. We're not really going to be using these Lorentz contractions much, and I don't think you'll be using them much throughout in your other courses, but these are such fundamental physical effects. It's important to remind you of them. Okay, so then we went on to discuss more of the structure of the group, and in particular, its generators. So we used this Taylor series expansion to get an equation for the generators of boosts. So you get these innocent-looking matrices of, you get entries of this type, off diagonal -1 in the two directions. And so then we get the picture that the boosts of Lorentz transformations in 3+1 dimensions are generated by these three matrices, K1, K2, and K3. So then we were studying the algebra of, because now we have all of the generators of the Lie algebra of the Lorentz group. We've got 3 boosts and the 3 rotations. And so we started studying the algebra, and we have that the commutator of 2 boosts is a rotation. The commutator of a boost and a rotation, if it's non-zero, is a boost. And you can check work out all of the relations yourself. Most of them are written down there. And we didn't quite write down a compact form of the algebra, which we're going to need in order to study these things called representations of the algebra. So in order to do that in a neat way, we actually have to redefine the rotation generators slightly by inserting these 2 minus signs. Oh, thank you. At least in the form that I had derived them with, I wasn't able to find a simple compact form for to write it down. But if you make this slight redefinition of the generators, the T's still satisfy the SU2 algebra, the SO3 algebra, sorry. But then the other commutation relations can be written in a much nicer form, and all of them use the epsilon symbol, epsilon ijk. Now, we're now going to make even further, well, sorry, I'll just go on to say what I did say at the end of the lecture yesterday. So we're doing this in order to we want to study representations, and in other words, there'll be realizations of this algebra by matrices whose dimensions are not 4 by 4. In general, there'll be n by n matrices, and we're going to work out in principle what those matrices are. And the point is that, as I mentioned yesterday, different particles in nature are described by different fields, and the different fields transform in different representations. So we want to understand these, we need to understand these better. Okay, are there any questions about that aspect of yesterday's lecture? Okay, so let's continue. So there's a further quote unquote simplification, which is another redefinition of the generators. So you see, once you have an algebra, you're free to redefine, make linear combinations of the generators of that algebra, however you know, for whatever convenient purpose you may have in mind. It's still the same algebra, just written in a different basis. So in particular, we want to take the sum and difference, normalized with a factor of 2, of boosts and rotations. What this achieves for us is that the sum of the boosts and rotations, namely the n i's, commute with the difference. And moreover, the n i's by themselves obey the Lie algebra of rotations, and so do the n tilde i's. Okay. Now, I write this on the. So really, this is an exercise for you. You must verify this. It's a little bit painful to check it in detail, but not too bad. So you see, that means that the ni's generate a copy of the SO3 Lie algebra, and the ni tildes generate another copy of the SO3 Lie algebra. So we have two independent copies which actually commute with each other. What that means is that the Lie algebra of the Lorentz group in 3 plus 1 dimensions is a direct sum of 2 Lie algebras, both of which are isomorphic to each other and isomorphic to the Lie algebra of the rotation group in 3 dimensions. Now, you know, we also introduced this concept that Lie groups are exponentials of their algebras. So in that context, what does this mean? So in particular, we were saying that SO3 elements of the group SO3 are exponentials of Lie algebra elements.
Would be direct products. Lorentz group would be direct products of SO3 times SO3.
Yeah, so naively, that's what you would think. But this is not the case, okay? And this cannot be the case because SO3 is compact. you know, it's spanned by these compact angles, all of which go from 0 to 2 pi. Whereas the Lorentz group, we've seen, is a non-compact space. It has directions which go off to infinity in the direction of the 3 boosts. So it's this non-compactness that means that this is not not the case. Now, the Lorentz group is the exponential of its Lie algebra, but its Lie algebra, if you write it in a basis in which the generators are all, let's say, oh, sorry, so someone coming in. Yeah.
For the electricity, oh, you already got it. Awesome.
Yeah.
Cool.
Your colleague must have been listening or in the other room. So
Good.
thank you.
Excellent.
Thank you. Thanks. Yeah, the point is that it is the exponential of its Lie algebra, but the way we've written this Lie algebra, it's combining generators in non-compact directions with compact ones. So even though the algebra is the same, the linear combinations of elements in this algebra, we're allowing them to go to infinity in certain directions. Okay. Later on, we might be able to see a different way of writing the algebra, which is more, let's say, natural from the point of view of taking the exponential. Okay. All right. So a representation of, so now I'm going to just explain what is a representation mathematically, okay? And then we're going to study some of these. So we saw that you know, we've got these matrices, the TIs, which satisfy the relations for the Lie algebra of SO3. So what they actually are is just a particular three-dimensional because they're 3 by 3, three-dimensional representation of the Lie algebra of SO3. Okay, as we're going to see shortly, there are many additional representations with different dimensions. So what we mean by a representation of the Lie algebra of SO3 of some dimension n, capital N, is simply a set of 3 n by n matrices which obey, under matrix multiplication, obey the relations of the Lie algebra of SO3. Okay, so to give a representation of the Lie algebra of SO3, you just have to give me 3 n by n matrices, R1, R2, and R3. And if you take their commutators and compute them, then they just have to satisfy this. And that's the definition of a representation. Is that definition clear to everyone, or does anyone have a question? Okay. So from that point of view, one can think of the algebra as an abstract quantity. So for a more general algebra, if we just, instead of writing commutator, we just write, you know, composition rule. If you have an algebra whose elements are some TAs as a basis for the algebra, so TA could go from 1 up to any dimension D, which satisfy this kind of relation where you have some, if you specify what these C's are and verify a few other properties, then these relations define some algebra. The C's are just some constants. Then a representation of that algebra would be a set of matrices which obey the same relations, but where the product rule is the commutator. Okay. So in other words, you just, for each of the TAs, there's a matrix RA. And you get this, mathematically you'd call this a homomorphism from the algebra to the set of n by n matrices. Now, so that's the idea of representation. It's, you just have some relations which define an algebra, or defined by an algebra, and then you want to represent those relations using matrices. Now, there's a notion of irreducibility in representations, okay? So the irreducible representations are the fundamental ones. You can build any representation out of the irreducible ones. These irreducible ones are the ones which you cannot simplify any further. I'll give you an example of something which is not irreducible. Let's consider for SO3 again, the following 6 by 6 matrices. So you just take the TIs that we had from the beginning and make a 6 by 6 block diagonal matrix, where the off diagonal 3 by 3 blocks are 0. Okay, these matrices, it's trivial to check almost, will satisfy the SO3 Lie algebra, the commutation relations of SO3. So therefore, this is a representation. However, this is obviously the sum of two more fundamental objects. It's the sum of the three-dimensional, the diagonal sum of the three-dimensional representation. So essentially, this notion of irreducibility means you can't find any basis for the vector space on which the matrices are acting on, or any basis of the algebra in which the matrices are not block diagonal. So reducible representations are essentially block diagonal sums of irreducible ones which cannot be made block diagonal themselves. Now, you're going to study the classification of representations of the rotation algebra in quantum mechanics, but since we're going to need it for the Lorentz group, I'm going to go through some relevant aspects of it now. So if we're thinking of SO3 as really rotations in our real three-dimensional space, of course, you could be thinking of SO3 acting on some other systems as well, and the representations would have a different interpretation. But if we're thinking of it as representations in our real three-dimensional space, then and we consider quantum mechanical systems that have rotational symmetry, for example, then SO3, the algebra of SO3 appears in quantum mechanics as the angular momentum algebra. And the representations describe states with different quantum spins, different quantized spins, let's say, okay? So the actual allowed values of the spins of a system, quantum system, take discrete values, okay? We'll see what those values are. And this discreteness actually just follows, it actually follows from the from the representation theory of the Lie algebra, it also follows from the fact that SO3 is a compact group. Okay, so this is at the bottom is the classification, I mean, a description of all of the representations, let's say. So every irreducible representation depends on a half integer, j. Let's say you can take it greater than or equal to 0 without loss of generality. And so for every half integer, there's a representation of the Lie algebra whose dimension is 2 times j plus 1. So let's, that means that there's some 2j plus 1 square, dimensional matrices. There's 3 of them, and this is what we'll call them, okay? There's R1, R2, R3, as we were saying, and they will always satisfy the algebra relations. So it's important to remember that these representations are given by matrices. So when I write this, I've suppressed the labels of the matrix labels themselves. So if I wanted to be a bit clearer, I could write it like this, where A and B go from 1 all the way up to the dimension of the representation, which is 2j plus 1. And as we know, I just runs from 1, is just 1, 2, or 3. Okay. Now, matrices are always, square matrices, whenever you think of square matrices, you should always think about a vector space on which they act. That's their role in life. And in the quantum mechanics setting, you thinking of the Hilbert space of different spin states. Anyway, from the point of view of representation theory, there's some vector space, V, whose dimension is 2j plus 1. In general, this is a complex vector space, okay? Because these representations turn out to be, in general, for Lie algebras, there'll be complex representations. Now, we've got freedom to choose a basis for this representation space. Ideally, you want to simplify the problem. You want to simplify the matrices that you're looking for as much as possible to begin with. So we know, because the matrices do not commute with each other, that they cannot all be diagonal. However, we can choose one of them. We can choose one of them to be diagonal. What this means is you're just choosing a basis for the vector spaces in which one of them is diagonal. Okay, and that's usually how the representation theory of Lie algebras proceeds. You choose, first of all, you figure out what's the maximum number of representation matrices that you can diagonalize without spoiling the commutation relations. And that's something called the rank of the Lie algebra. Now for SO3, the rank is 1, and so we can diagonalize just one of the 3 matrices. Okay. Now, so in this basis, it means that the eigenvectors of the matrix, we can think of them as a basis for the vector space itself. And it turns out that the eigenvalues, so once you've completed the representation theory, which is what you'll be doing maybe next week or the week after in quantum mechanics, so I don't want to duplicate the lecturing effort, but you'll find that this j, this half integer j, you can order the eigenvalues starting with j at the top, and then the next eigenvalue is j minus 1, then it goes j minus 2, all the way down to minus j. So this is 2j plus 1 numbers. So for example, if I take the first non-zero half integer, which is a half, I get that in the two-dimensional representation, that T3 is represented by the matrix, the diagonal matrix 1 half minus 1 half. If I take the next half integer, if I add another half integer, I can take j equals 1, and in that representation, the diagonalized form of T3 is 1, 0, minus 1, meaning that the spins in that representation are, you have spin 1, spin 0, and spin minus 1. And similarly, you can carry on like that forever. Now, the way you get these spins is by, you have to use the algebra and so on. I mean, you use the algebra in a clever way, and that way is what are called raising and lowering operators. Oh, yeah, by the way, note that this is our, in this diagonal form, this is, in this diagonal basis, this is at the representation of T3. If you remember, in our three-dimensional presentation of the Lie algebra, T3 was not diagonal, it was anti-symmetric. But the point is that what I've done here, if you look at these matrices, I've actually chosen a basis in which the matrices are Hermitian, because the eigenvalues are real, whereas our T's were anti-Hermitian because they're anti-symmetric. So they don't even have real eigenvalues. So to go from one basis to actually compare this basis to the one we were using would involve taking, for example, x and y and writing something like x plus iy and x minus iy, so complex coordinates. And that would be a basis in which T3 did turn out to be diagonal. But it would really be, you'd really have to map this to I times T3. But that's just an aside. Related to that is the following. So traditionally, physicists will pick a basis in which, pick a presentation in which the generators are Hermitian, because the diagonalizable generators, their eigenvalues will turn out to be physical observables. So this is what we will consider for now. And as I said, we then choose A3 to be diagonal. And these raising and lowering operators are just complex linear combinations of A1 and A2. Okay. And they have the property that if, say, psi is some eigenvector in the representation space. It's just one of the eigenvectors of the diagonal operator. So that A3 on psi is the spin, which is M. Then if you look at, instead of looking at psi, you look at A3, you look at A plus times psi. A plus times psi is just some other vector. But you can use the algebra, the SO3 algebra, to show that A plus times psi is also an eigenvector, and it has a spin which is one integer bigger than the one you started with. Similarly, A minus has a spin which is decreased by 1. You see the fact that the eigenvectors are increasing and decreasing the spins by 1, precisely 1, is related to the fact that the spins have to be quantized. Doesn't make much sense that you've got a spin which is, say, root 3 over 2, and a spin which is root 3 over 2 plus 1, and so on. So from that, you can, just from these simple relations, which follow very easily from the algebra, you can see that the spins have to be quantized. And moreover, since by assumption, the vector space is finite dimensional, this process has to stop somewhere. You can't keep increasing the spin by 1 unit every time you apply the raising operator A plus. So there must be a vector somewhere such that A plus acting on it gives you 0. Which means that there's going to be a maximum spin and a minimum spin. And clearly, this choice here, I could have swapped the roles of A1 and A2, or swapped the signs as well. So clearly, the maximum spin is going to turn out to be the minimum spin as well, just based on symmetry. But you can also, by brute force, demonstrate that. So that's why the matrices take this, that's why the spins take this form. You see that the minimum spin, so in the two-dimensional, in the spin half representation, you have minus a half and plus a half. The maximum spin and the minimum spin are the same. This is a minus 3 halves in the bottom here. Okay, so in the end, you're going to do all the details of this much more carefully in quantum mechanics, but thinking in a quantum mechanical language, we can sort of write a bra and ket notation to label the states. So the representation is labeled by the highest spin, which is J, and then the different spins are labeled by M. And then we determine the entries of A, which remember is I times, is the square root of -1 times the R's, by just computing the matrix element, because you have an orthonormal basis. So this is called the Wigner representation. So we're not deriving these formulas, but you will derive them in the quantum mechanics course. So now you can think of M prime and M as the matrix elements, the matrix entries of the big matrix. Okay, and this is an explicit formulae telling you what they are. I'll show you how to apply this formula in a second. So delta here is just the Kronecker delta, which is just a matrix representation of the identity matrix. So it's this will always give 0 unless the two indices of delta are the same. So it's, in other words, just an index notation for writing the identity matrix. And that's it. So let's consider trying to use this formula in the case j equals a half. So j equals a half, so 2 times j plus 1 is 2, and that's the two-dimensional representation that we claim exists. So now the way these formulas are written, it's a bit funny because j equals a half means m prime and m take values plus or minus a half. But we should think of a matrix acting on, the plus state is the first row and the minus a half state is the second row. Okay, so the 1, 1 entry of the matrix would be when m prime equals m equals a half. Okay, so if I set so yeah, if I consider values of m prime and m which are equal, that means I'll get the diagonal entries of any of the matrices. But you can see that because of these, this shift by 1 here and a shift by -1 here, those entries will always be 0. So the A1 and A2 are always off diagonal. Okay, so now let's consider the 1, 2 entry of A1. So in this case, 1, 2 would mean m prime is a half and m is minus a half, because 1 corresponds to spin a half and 2 corresponds to spin minus a half. So now m prime is a half and m is minus a half. So you see that you get a non-zero entry from the first guy because you've got delta of a half, which is 1. Whereas you don't get anything from here. So now we put in the values. So j is always a half, and m was minus a half. So I get a half minus a half from here, which is 1. And from here, so this gives me 1. And then here I get 1 half minus a half, which is 0, plus 1, which is 1. So this factor contributes exactly 1 times the overall factor of a half, which is over there. So in other words, it means that the 1, 2 entry of the matrix is 1 half. Okay. Similarly, the 2, 1 entry of the matrix is 1 half. And that will come from the second term as opposed to the first term. And you see that these factors are all the same for A2 as well, except A2 just has a minus I and a change of sign between the two factors. Okay. So you see this is important and this is important. So if you compute A1, you've already computed A2 because the terms are the same, except you just have to keep track of this sign and this minus I at the front. Good. So let me just clear this. So if we proceed like that, for j equals a half, what we end up with is, oops, that's wrong. Is 1/2 times the Pauli matrices from these formulae. Yeah, sorry, the thing at the top here means for j equals 0, 2j plus 1 is 1, and the AIs will all be 0. So that's called the trivial representation. And all the algebras have such a thing. So it's a one-dimensional representation which is trivial. It's trivial, but however, it's extremely important because it means that it's a representation of which is invariant under the action of the, in this case, SO3. And physics is all about invariance. So when we are working with wave functions or with fields, you know, actually, well, if you can see my t-shirt, it contains lots of fields. And these fields transform in all these different representations of the Lorentz group. But the quantity which is written down is a combination of those fields, which is invariant under Lorentz transformations. Oh, I'm kind of, sorry, I'm getting a bit carried away and I'm losing track of time. And also my voice is suffering from all this talking. So let's take a little break, and then when we come back at on the hour, we can take some questions and we'll continue a little bit further before stopping for the day. All right, let's have a break. Welcome back. So yeah, we were looking at the at this two-dimensional representation of the algebra of rotations, which is given in terms of the Pauli matrices, and more precisely 1/2 times the Pauli matrices. And this 1/2 actually will turn out to be quite an important factor. So what I want to do is go back to what I want to do is give an interpretation. We want to understand, what is this representation? What does it mean? So in our original geometric basis, we had the 3x3 T matrices. And each one corresponds to rotations around the corresponding coordinate axes. So to map precisely back to the T's, we have to remove this factor of I, because our T's are anti-Hermitian, whereas the Pauli matrices are Hermitian. And with that factor of I, what we see is that Tj corresponds to I times 1/2 of the Pauli matrices, Pauli matrix T sigma j. Now, in the way we derived the representation, the three-dimensional representation before, was thinking of it geometrically as rotations in three-dimensional space, or if it's or more generally on just some three-component vectors. But if we're thinking about rotations in three-dimensional space, we can then ask, we've got this other representation, which is now two-dimensional. So since the three-dimensional representation acts on, for example, the coordinates of space, or vectors in three-component vectors in space, what are the objects that the two-dimensional representation acts on? So what are the two-component objects? Just put that in, they're just two-component vectors. But what is their interpretation? What are the two-component objects that this representation acts on? So these two-component vectors, they have a name, and they're called spinors. And we use spinors to describe fermions. In other words, you will have heard about the spins of fermions like electrons and quarks, and we always say that they have spin a half. Well, that's because if you write down the wave function for a fermion, if you do it carefully, it's actually described by a spinorial function. Or when we go to fields, we talk about spinor fields. Okay, now I just want to elaborate that a little bit. So if you recall that exponential of theta 3 T3 is this matrix cosine theta, it's minus sine or plus sine. So make sure I'm not changing conventions. Oh, there it is. Sine, sine minus sine cosine. So this is what we had before. So now we can actually compare that to exponential. So the corresponding matrix which corresponds to exactly this same rotation, but now in the two-dimensional representation. So to do that, we would just we write down θ3 multiplied by the corresponding generator. And that generator is I sigma 3 over 2, which is exponential of θ3 times I 0, 0 minus I over 2. Now, if you do the Taylor series expansion, you can check, and this is equal to the following matrix. So it's a diagonal matrix, which is unsurprising because sigma 3 is diagonal, and its entries are pure phases of the form e to the I θ3 over 2 for the first one, and then you get minus, you get the complex conjugate in the other entry. Okay, why is that interesting? So this thing was called R. Let's call this thing R3 of θ3. Well, no, I mean, in the previous notation, it was R of 0, 0, θ3. Okay, so if I shifted θ3 by 2 pi, it remains invariant, which is obvious because if I just take the 3 direction and I make a 2 pi rotation around it, I come back to myself, and then any vector will return to itself. Let me define this thing as m of 0, 0, θ3. Now, if I do the same thing in this two-dimensional representation, I get a minus sign because of the factor of 2. So fermions change sign. I mean, not fermions, but spinors. So I'm putting an exclamation mark there because this is pretty strange phenomenon. I mean, it's unintuitive because if you would think if you make a 2 pi rotation in space that physics will be invariant. So in a way, this is how we define fermions. They are the wave function of a fermion will change sign if you make a 2 pi rotation in space. Now, going back to here as well, I want to finish by looking at this matrix, this 2 by 2 matrix M. When we're talking about the Lie algebra of SO3, and then we take this exponential, we get an orthogonal 3 by 3 matrix. Now, there's clearly a correspondence between this matrix R and the matrix M in some sense, right? I mean, the algebras are the same, but what are we doing when we're exponentiating these combinations of Pauli matrices? And what's the relation between these things? Well, the point is that so if you consider a general linear combination of theta j I sigma j over 2, then this looks something like well, I don't need to write it down, but if J is of this form, it is a general anti-Hermitian matrix. General anti-Hermitian 2 by 2 matrix with 0 trace. Maybe I will write it down. Which is my so so this is what anti-Hermitian means. You take the transpose and the complex conjugate operation, just for definiteness. And we see that the Hermitian conjugate J dagger is equal to minus J, and that the trace of J is 0. So any anti-Hermitian traceless 2 by 2 matrix can be written in this way. So what about the exponential of J? Maybe write as M of J. Well, M of J satisfies M dagger M is equal to the identity matrix, and that the determinant of M is equal to 1. So matrices which satisfy this property, so this is very much like the orthogonality property that we had for the 3x3 matrices, but involves complex conjugation and complex matrices at the same time. So such matrices are called unitary. And here we're looking at a class of unitary matrices whose determinant is equal to 1. And these are called special unitary matrices. So M will always be an element of another group, which is called SU2. So, and you know, SU2 is a very important group in physics, and I'm sure that some of you have come across it before. As an aside, maybe I'll just say, you can, you know, consider unitary n by n matrices. These would be n by n matrices which satisfy the same sort of condition. Running out of labels now. I'll call them M, N. Actually, I'll write it with a lower label. And if you add the determinant 1 condition, you get the special unitary group. And we also need to be familiar with these groups in order to understand the standard model, for example, which is based on a symmetry group which involves SU3, SU2, and U1. So these groups occur in different places in physics. So we've just seen that SU2 and SO3 occur when we're considering rotations in space, but they also occur in other places and have different roles in those places. So it's important to not get confused about where they show up and keep track of the objects on which they're acting on. Okay, so what this means, one thing that what we've just shown or discussed means, is that the Lie algebra of SU2 is the same as the Lie algebra of SO3. But SU2 and SO3 are not the same. But they are almost the same. And that goes back to this discussion here. SO3 group elements, when theta goes from theta to theta plus 2 pi, for any of the thetas, you have to come back to the same group element. Whereas SU2 does not have that requirement. When theta goes from theta to theta plus 2 pi, you can have a -1. In fact, you know, in the three-dimensional representation of SO3, so 3 by 3 orthogonal matrices, special orthogonal matrices, there is no -1 for the special orthogonal group, because minus the identity has determinant -1. So all of the elements, I mean, so there's a map between the group SU2 and SO3 up to minus the identity in SU2, which is what you get whenever you take one of the angles and shift it by 2 pi. So, in fact, that means if I took this element out of the group, quote unquote, what you can do is consider an equivalence relation such that minus the identity is mapped to the identity element, then you will get SO3. And this plus or minus 1, you can think of it as a subgroup of SU2 of order 2. So Z mod 2 is the simplest non-trivial group with 2 elements. So I think I'll stop there, and we can take questions.
Professor, I had a question about what exactly means to complexify the Lie algebra.
That's a good question. So the basic point is that you see this representation over here, for example, just as an example, the 2-dimensional representation, it involves complex vectors. So the point is that if you worked only over the reals and you fixed all of the generators to be, say, Hermitian or anti-Hermitian, whatever you're out, depending on whatever your algebra is. Let's say Hermitian, and so that everything is real in some sense, and you only used real vectors spaces, you would not find all of the representations. In fact, you would find very few. So the representation theory of Lie algebras is done over the complex numbers. And we know also, you know, in quantum mechanics, wave functions are complex Hilbert spaces are complex. So this is fine. And quite natural.
Right, but when we complexify the Lie algebra, does the dimension of the representation space change?
No, so I haven't really complexified the Lie algebra, actually. So I've got a three-dimensional Lie algebra, which is the SU2 or SO3 Lie algebra. And I've looked at its representations. But in order to look at its representations, I'm looking at vectors which are complex.
Right.
That's not the same thing as, because there's another notion of complexifying the Lie algebra, which is you take the generators and then you sort of double the dimension by roughly, when you go from x to x plus iy, you generate a space which is twice the size. And it has a real part and imaginary part. There's a way of doing that for Lie algebras. You can go from generators to generators plus some, if you have some appropriate notion of what I is, generators plus some new generators times I. And that would be a complexification of the Lie algebra. And you would get an algebra which is twice the size.
No, right.
So, yeah. For SU2, for the SU2 representations we've been talking about, we're just looking at vector spaces on which the representations act, which are complex. Even though you can find, a Hermitian basis for the algebra, if you want.
Right. I had another question about the spin state space. Because for j equals 0, that means the spin 0, and so the spin state space just reduces to the complex numbers, right?
Yeah.
Yeah. So when you talk about a particle with spin 0, you don't really need to talk about their spin because it's their Hilbert space is the orbital state space tensor product spin state space, but if the spin state space is only the complex numbers, then it's basically the same as only the orbital state space.
Yeah. So the spin doesn't play much role there.
Right.
Describe the state because it has no spin. Later on in the course, when we introduce what are called scalar fields will be fields which represent particles of spin 0. And so, yeah, and the Higgs field is an example of that in nature.
I had one last question about the bibliography for this part, because I don't know if this is in Landau.
Oh, this is probably not in Landau Lifshitz. I mean, I just wrote this, I just wrote this up without thinking about a reference for it. But the notes themselves, will contain it. But there's lots of references for this. But I don't want to. So this is not a course on group theory. I don't want you to all get bogged down in that. But at the same time, I want you to learn group theory in some sense. So, okay, ask me that. Ask me that again. Well, in fact, I was going to suggest for the students that are actually here, maybe we can just briefly meet each other in person, like today. Is that possible? Who is actually here? How many of you are there now?
I'm here.
I'm
Sorry?
here. Me too.
1, 2, 3. Case?
I am here.